So we're going to start in with chapter 8, which is chemical reactions. Okay, the first thing we've got to do is really define what is a chemical reaction. Can anyone give me kind of a base definition of a chemical reaction?
There's a change in molecules and it makes something happen.
Makes something...
Change.
No.
React.
What? It makes something new, right? A chemical reaction happens when something new is made. So a process by which one or more substances are changed into one or more different substances, right? Something new is formed. That's the difference between a chemical change and a physical change, right? A chemical change is spelled out by a chemical reaction, and it tells us that something new is formed, okay? Okay, I want to make this one little extra note here that chemical reactions are represented by what's called a chemical equation. And a chemical equation is just that, right? It's an equation that shows us what's happening in the chemical reaction. So you'll hear me use those terms kind of interchangeably, right? A chemical reaction is what's actually happening, right? The mixing and the making of new things. But a chemical equation is just the way you write it out, right? It's just the way that you represent what's happening in the chemical reaction. So a chemical equation is just the written form, right? The written version of a chemical reaction. Okay, and a chemical reaction or a chemical equation is made up of two distinct parts. Do you know what they are? One's on the left side and one's on the right side of an arrow. The products and the reactants. Very good. Okay, so the reactants are what we start with. Okay, the reactants are the things that you begin with. Okay, things that we start with. They are the things that are doing the reacting. Okay, reactants go on the beginning side, the left side of the arrow. The products are what is made, right? What is produced. Okay, so the products are what is being made. All right, the very kind of basic format of a chemical reaction looks like this. Something A plus something B yields something C and something D, right? These A, B, C, and D just represent different chemical compounds. And so what does that arrow kind of represent? Do you remember what that means? Kind of change. What else does it mean? It's similar to an equal sign, right? It's similar to an equal sign. These two compounds put together equal these two new compounds, right? That's kind of what that means. But really that arrow means yields or produces, right? These two things put together will yield these two products, right? Or one product, whatever. There can be one reactant to one different product. There can be one reactant to two products, two to one, two to whatever. There can be as many things on each side as you want, okay? Or as is necessary. But that's what a chemical reaction in general looks like, okay? So now we're going to start answering some questions. How do we know that a chemical reaction has taken place? How do we know? And I kind of categorize 4 main indicators, and they're kind of listed there on your slides. But what is it that we know has to happen for a chemical reaction to take place? Or what is a signal for us that a chemical reaction has taken place? Yeah. Okay, what do you mean by a physical change? Okay, good. A change in color. Okay, that's the first one. A color change indicates to us that a chemical reaction has taken place. This happens like when the leaves change color, right? When rust forms on a vehicle or some sort of metal, right? That's a chemical change. So if you mix two clear things together and you get something yellow or something pink or whatever, that has to tell us that a chemical change has taken place. Okay, Joe, what else? Change in temperature, good. That's about 2 phases down, but yes, a change in temperature is one. I'll get to that, okay? If you put two things together and they start releasing heat or they start getting colder, that's a good clue for us that a change has taken place. This one right above that is production of a gas. So if things start bubbling, okay, without the implication that it's boiling, right? If I put two things together and they start bubbling, that's a good clue for us that a chemical change has taken place. Do you see this in everyday life? When you put two things together and they start bubbling, what example can you come up with for that? Okay, kind of like soapy water. A little bit. I'm thinking of another cleaning process, maybe used it in middle school science. You take baking soda and what do you put with it? Vinegar, and what happens? It bubbles up, it starts to foam, right? That's a chemical reaction, okay? So that process is two things that are, seemingly stable on their own, but when they mix together, you see that production of a gas. We talked about this a little bit when we did chemical and physical changes at the beginning of the year, but what are some things that we can see hot or cold really quickly happen via a chemical reaction? We talked about these a little bit. Yeah, hand warmers, good, right? Hot hands, you have to get them shaking to start to warm up, right? Those interaction of those particles causes a heat. And then the ice pack that you have to pop, right? That's a good clue for us that's happening as well, okay? Glow stick, same thing, right? That light glow comes from us snapping that inner capsule, and then that allows that chemical reaction to happen. Yep, very good. The last one's called the formation of a precipitate. Okay, any idea what a precipitate means? Okay, a precipitate is a solid that appears after two or more liquids have been mixed together. Okay, so I put two liquids together and I get something chunky out of it, right? That would be a clue for me that there's a chemical reaction that's taken place. Okay, if I mix two liquids together and it doesn't look like anything's happening, it doesn't necessarily mean there's not a chemical reaction, but it doesn't mean that there is one either, right? We're unknown. So these things are indicators for us, right? They indicate for us for sure that a chemical reaction has happened. Okay? So now that we've got an idea about what a chemical reaction is, we've got to figure out how do we write out a chemical equation? How can we represent that chemical reaction, okay? When we write out an equation, we have to write out everything we know about it. We have to write down everything that's a product and everything that's a reactant. And we have to have correct chemical formulas. So when we did all that stuff with naming in the first semester, that's all going to start coming back, okay? And we're going to start getting really good at naming molecules again. Being able to write out the formula for calcium chloride, right? Can you write out the formula for lithium nitrate, right? Those are things that you're going to have to be able to do again, okay? Here's the issue, right? If I was going to write out a formula and I needed sodium sulfate, right? Sodium sulfate is Na2SO4. Okay, if I needed sodium sulfate, Na2SO4. But when I'm writing the problem, I only write Na and I accidentally write SO3. When I go to balance my reaction, it's not going to work, right? Because my formula is incorrect. So when I go to see, do I have the same number of sodiums on both sides of my reaction, and I have the same number of sulfurs and the same number of oxygens, it won't work, right? Because I have an incorrect formula. So we have to be really, really careful about writing out correct formulas. Okay? The law of conservation of mass must be satisfied. That's the most fundamental part of balancing chemical reactions, is that we are satisfying the law of conservation of mass. Can anyone tell me, what does the law of conservation of mass say? Mass is neither created or destroyed, okay? Atoms are neither created or destroyed during chemical reactions. So all that means for us is that the same number of atoms of each element must appear on each side of a balanced equation. Okay, the same number of atoms of each element have to appear on both sides. Okay, so that means if I put in 4 hydrogens to my reaction, right? If my reactant's side has 4 hydrogens, my product side has to have 4 hydrogens, right? The hydrogens are not going to disappear to somewhere, and they're not going to appear out of nowhere, right? They have to have the same number on both sides. That's our goal when we balance equations. We're going to write out what our products and reactants are, and then we have to figure out what's the ratio they need to combine in order for it to be balanced. Okay, that's our job, is to really find out the ratio. Okay? When we're writing out chemical equations, some elements in their pure form or in their most basic form cannot exist as single elements. They have to exist as a pair, like with another of their same kind, okay? These are called diatomic molecules. Diatomic molecules. There are 7 of them, 7 diatomic molecules. So I'm going to make a list here of those diatomic molecules, and I want you to write them out, because if a reaction calls for nitrogen, for example, we don't just get to write N. Nitrogen is diatomic, so nitrogen gas is really N2, right? It is in a bond with another of its own kind. So nitrogen is diatomic, oxygen is diatomic, fluorine, chlorine, bromine, iodine, and hydrogen. Okay, those are the 7 diatomic molecules. 1, 2, 3, 4, 5, 6, and 7. Okay, I want you to locate those on the periodic table. And if you don't have your own periodic table up, that's fine. Look up on our periodic table up here. Find out, where are those molecules? You see nitrogen right here? Okay, nitrogen right there. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. What does that make? What'd you say? An upside down L, or a... It makes a 7. It makes a 7. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Doesn't that make a 7? Which is an upside down L, I would agree. Okay, but doesn't it make a 7? Yes or no? Yes, it does. How does it not make a 7? I'm ignoring hydrogen. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. It seems like a 7. Okay, seems like a 7 to me. Okay, so if you can't remember what the diatomic molecules are, you start with nitrogen and make a 7, and then you add hydrogen in with it. Okay, so there's our diatomic molecules on the periodic table. Okay, 7 of them that make an upside down L. Okay?
Is that a 2 or is that a Z?
What?
Is that a 2 or a Z?
What do you think it probably is?
A 2, but the N, one next to the N is a Z.
Okay, but what do you think would be the most appropriate thing for it to go there?
A 2.
Probably a 2. I would agree. Yeah.
I've been writing Z.
All right, very good. Here's some symbols that you might see in chemical equations. If we see S, L, or G in parentheses to the side of a molecule, those just mean it's what state of matter that compound is in. So if we see an S next to it, that means that compound is being mixed as a solid, right? Or it's being produced as a solid, liquid, and gas. The next one is AQ. Do you know what that means? It means it's an aqueous solution. Thank you very much for reading that. What does that mean? Okay, yes, I can read what it says. It means it's been dissolved in water, okay? So when we see an aqueous solution, that means that our compound is not a solid or a liquid. It's just been dissolved in water, okay? So it's been ionized or broken apart, right? It's dissolved. A single-headed arrow like that means a yields, like we talked about before, yields or produces. And then if you see a double-headed arrow, that means that we have a reaction that's reversible. So it can go to the products, and then those products now become the reactants, and it goes backwards. Then it goes again. We don't work with those a whole lot, but if you see that, that's all that means, is it is reversible. Okay? So here is a really basic chemical reaction, right? Potassium chlorate will break down or yield 2 smaller molecules, potassium chloride and oxygen gas. And so why is it not just O? Why is it O2? Because oxygen is a diatomic molecule, right? It's a diatomic, okay? So not just O, but O2, okay? What do you think these numbers in front of the chemical formulas are called? This 3 and this 2 and this 2. What do you call those numbers?
Coefficients.
Coefficients, good. Just like in math, 2x, right? 2y squared, whatever it is. These numbers in front are called coefficients, okay? And we use those to help us determine our ratios. How do these molecules need to go together, okay? So let's look at our next one. We're going to talk about coefficients. We need a way to represent more than one molecule of a compound to satisfy the law of conservation of mass, okay? So if I see 2H2O, that means I have 2 water molecules. So how many hydrogen atoms would I have in this formula right here? If I have 2 water molecules, how many hydrogens do I have? Say it with some confidence here. How many? 4, good. And how many oxygen atoms would I have? 2, right? Oops. So all I'm doing is multiplying that coefficient through. right? 2 times 2 hydrogens is 4. And then if there's no subscript listed here, what do we assume is there? A 1. So, right, 2 times 1 oxygen is 2. Are we feel comfortable with that? Being able to identify that part? Give me a yes or a no. Okay. Coefficients also represent the relative number of moles in a chemical reaction. So when we look at a chemical reaction here, if I speak through this chemical reaction, it says 1 molecule of C10H8 reacts with 12 oxygen gas molecules to produce 10 carbon dioxide molecules and 4 water molecules. Right? That's what we're talking about here if we look at it on the molecular level, so individual molecules. But the way we use it more often is actually on the molar level, right? Talking about a big quantity of them. So I say it the same way. What coefficient do we assume is right there? If there's nothing listed there, we assume it's a 1, right? So it says 1 mole of C10H8 reacts with 12 moles of O2, produces 10 moles of CO2 and 4 moles of water. Okay? It's the same exact ratio, except we don't deal with it on a molecular level, right? I want to deal with it in grams and actual quantities that I can see and work with. And so when we talk about those coefficients, we're usually going to consider them in terms of moles, right? 4 moles of water was produced. Okay? For bonus points here, can you tell me how many of anything is in 1 mole?
6.022 times 10 to the 23rd.
Very nice, with confidence. Okay, 1 mole is equal to 6.022 times 10 to the 23rd molecules of anything, right? So rather than deal on the molecular level, I'm talking on the molar level, a big quantity of those, so I can actually kind of see it and understand what it's looking like. Okay? All right. How many moles of each are there? We're just looking at the coefficient. So 1 mole of C10H8, 12 moles of O2, 10 moles of CO2, and 4 moles of water. All right, a couple notes before we actually get into the balancing, okay? When we balance equations, we're going to balance each atom one at a time, or each element one at a time, I should say, okay? If you have a polyatomic ion that appears on both sides of the equation, you can keep those together. So let's remind ourselves, what are polyatomic ions? Multiple, many, yes, I would agree here, but what is a polyatomic ion? Can you give me an example or tell me where am I going to find the polyatomic ions? In the box, right? The box tells us ions with many atoms, right? So phosphate, nitrate, carbonate, all of those things that we got familiar with using when we were naming compounds, those are polyatomic ions, okay? So if you see phosphate on both sides of our equation, we'll be able to balance that as a whole, okay? And that will make more sense as we look at an example, okay? Balancing equations is kind of like a puzzle. It might take more than one try to get to your final answer. I'm going to recommend that you do balancing equations in pencil for that reason, okay? Because it might take a lot of back and forth. But the good thing about balancing reactions is that there's only one right answer. I mean, just like most things in what we do, there's only one right answer. And there's no reason you should ever miss a balancing equations point, right? Because you can always go count your atoms and make sure that they are the same on both sides, okay? So there's always a way to check your answer. Okay, let's look at this first equation here with HCl. This is written for some reason real small, but let's look at it. Our first reaction says H2 plus Cl2 yields HCl. Does that reaction look like it's balanced to you? Yes or no? Are there the same amount of hydrogens on the left and on the right side of the reaction? No. Okay, so what has to happen here? Can I do this? Can I put a 2 and a 2 like that? No. The only way that I can edit a reaction is by adding a coefficient. So if I put a coefficient here, will that help me balance? No. Where does it need to go? The HCl. By putting a 2 there, that means that I have 2 hydrogens and 2 chlorines. Right? It would be like me just rewriting another HCl right here. That would give me 2 hydrogens and 2 chlorines. Okay? But the only All right, things to remember. We never add coefficients in the middle of a chemical formula. They always go in the very front. So in that one, for example, if I needed 2 Cl's but not 2 H's, I can't go like this. Right? That doesn't make sense. You don't put a coefficient in the middle of any term, right? We put it at the very beginning. Okay? Double check your chemical formulas to make sure they're correct. We can never change subscripts in a correct chemical formula. So like I tried to do with the other one, I can't do this H2Cl2, right? That's not what I do. I only add coefficients. Okay? And then the very last thing says you can reduce coefficients at the very end if they're all reducible by the same number. They're all reducible by the same number. Yeah, perfect. Okay, so at the very end, if we have coefficients that are 2, 2, 2, 4, right? Those are all reducible by the same number, and we'd bring them down to 1, 1, 1, 2, right? If they were reducible by the same number. Okay. This one here. Okay, we're gonna balance the equation. I'm gonna show you my method for balancing equations, kind of the format I follow, okay? When I see my reaction like this, I make a list of all the elements present in the list, okay? Something like this. Copper, silver, and then this is what I was talking about earlier. If I have a polyatomic ion on both sides, is NO3 present on both sides? It didn't get broken apart. It didn't get whatever. It is NO3 on both sides. Would we agree with that? Yes. So I'm going to keep NO3 together in my list. Rather than doing N and O, I'm going to balance NO3 just like as if it's its own thing. Does that kind of make sense? I'm going to keep that together. I make a list on the middle, and then I give myself a workspace on the left and on the right. And this is for me to be able to count my atoms and make sure that they are balanced. So all I'm going to do to start my problem is to count. How many of each am I starting with? Okay? So I want you to tell me, on the left side, how many coppers do I have? 1. How many silver do I have? 1. On the left side, I only have 1. This 3 only applies to oxygen, okay? And actually, it's part of our nitrate, so don't even worry about it, okay? So silver, I have 1. And how many NO3s do I have? Just 1, okay? I don't have 3 of them because I'm treating NO3 like it's its own thing, right? And there's no parentheses outside of it, so there's just 1. Is everyone on the same page with that? Okay. On the right-hand side, how many copper do I have? 1. How many silver? And how many nitrate? 2, right? This 2 applies to everything within the parentheses. So now I'm going to check my list. Is my equation balanced as it is? No, right? Because my numbers here don't match. Copper does, silver does, but nitrate does not. So how can I get myself to have 2 nitrates on the left-hand side? What do I need to do? Add a coefficient, but to which one? Okay, and what coefficient do I add there? I have to add a 2. Okay, I added 2 because now I'm making that 2 distribute throughout the whole molecule. So by adding a 2 here, how many silvers do I have now? I don't have 1 anymore, I have 2. And how many nitrates do I have? 2, right? So when I add a coefficient, I go and I recount that side, right? If I've got a 2 here, now that makes it 2 silvers and 2 nitrates. You see how it affected 2 different molecules there, 2 different elements? And so now I've got to go back and check my list. Copper is still balanced, but silver is not balanced anymore. So what do I need to do on this side to make it balanced? Okay, and what coefficient am I going to add right here with silver? 2. And so then I can change my list, right? And I recount, and I know that I've got 2 silvers there. Then I just go check, right? My coppers are balanced, my silvers are balanced, my nitrates are balanced. Okay? You will find that when you do these problems, you'll bounce back and forth from one side to the next, right? What I'm going to really suggest is that you change the coefficient first and then see how does it change my list. Don't try to balance your list and then work up from there, right? Change your coefficients and then count again. Okay, the bottom part is just workspace. But if you try to change the lists and balance them first, you're gonna get confused, I think. Okay? Yeah. Aluminum solid plus bromine liquid yields Al2Br6. Now, the solid, liquid, solid, these abbreviations right here don't change the way we balance it, right? It just gives us more information about the elements, but it doesn't change how we balance it. So I'm going to make my list. If you feel like you can balance it without using the list system, fine with me, right? I'm just giving you kind of a process to be able to see it all the way through. All right, so I make my list, and then I just do an initial count. So how many aluminums do we see on the left? 1, and how many bromine? 2, right? That 2 there tells me I have 2 bromines. Agreed? Okay, how many aluminums on the right-hand side? 2 and 6. Okay, so now I'm starting my reaction with none of them balanced. But look over here on the left. If I change one of them, it's not going to change the other. So it doesn't really matter which one I start with. Okay? How do I make aluminum balanced? What coefficient do I need to put with aluminum here? 2. And I recount, and I say now I have 2 aluminums. And then what coefficient needs to go here to make it balanced? Okay, a lot of us, did we come to the conclusion it's 3? Right? Because 3 times 2 would give me a total of 6. And that's where I would see it's balanced, it's balanced. Okay, how do you feel about that? Is this easy enough? You feel like it's review, that you've done it before? Okay. All right, I want you to try those next 3 on your own then, and we'll see if we agree. So I'm going to give you a couple minutes to finish. Try these next 3 on your own. If I'm looking at this reaction here on the bottom, we talked about this one on the previous one, but my oxygens here will never be an odd number, right? I will never have an odd number of oxygen, no matter what coefficient I put there. And so over here, here's my odd... Oops. Sorry, okay. Here's my odd oxygen out. Okay? So based on my information down here, I need 6 hydrogens, but I only have 2. What would I put there? 4. It would, okay, here's the thing. It would call for me, right? If I only have 2 hydrogens, but I need 6, it would call for me to put a 3 there. Would we agree with that? To get my hydrogens balanced. Yes? But here's the problem I run into. I know that this needs to be an even number, right? In order to make my oxygens even, it needs to be an even number. So instead of 3, I'm just going to double it to a 6. Okay? I'm going to double it to a 6. And I'm going to recount. That affected my hydrogens and my oxygens here. So now my hydrogens on the right-hand side are 12. And my oxygens on the right-hand side are 2 plus 6, which is 8. Okay? I am not going to bother balancing this oxygen until the very end, because whatever coefficient I put there, it's not going to affect anything else. I want that to be the last thing I change, okay? So I'm going to go look back at my list and say, what's another change I could make? Well, I know that my hydrogens are not balanced yet, so I'm going to go ahead and change here. What do I need to put here to make my hydrogens balanced? A 2. And that makes my hydrogens now 12. But what other element did it also change? The carbon. And so now I don't have 2 carbons anymore. I have 4. Okay, so now I'm going to bounce over to this other side and say, okay, I only have 1 carbon, but I need to have 4. So what can I put here? A 4. Okay, that changes carbon to 4. But what does it also change? Oxygen. So I need to recount the whole side. 2 oxygens times 4 is 8 plus 6, which is 14. And so now what can I put there to get to 14 oxygens? A 7. Okay, do you see how that made us kind of take a leap at the beginning? If you didn't put those dots together at the beginning, like by putting the 6 there right away, no problem. You would have just taken a couple extra steps. That's okay, right? It might take you a lot of back and forth before you get there, and that is just fine.